In the last video, we looked at the definition of linear operators and we introduced the Laplace transform. In this video, we'll use the Laplace transform to transform differential equations and use it to show how we can solve those differential equations. Let's begin by going over a proof that we didn't show in that last video. We had mentioned that the integral form of an operator was also a linear operator. So we introduced this form. We said that the operator was the integral of the original function multiplied with another function in this other variable s. So s becomes the variable of the operator. And we hadn't proved that this is a linear operator, but we'll do that here. So if we define this as our linear operator, then if we take two functions, f1 and f2, and we multiply those by the constants a and b, and we perform the operation on that sum, then we can expand as follows. So just substituting the definition of that operator here, we can then, we see here we are multiplying g of s by each function and integrating over time. And then obviously we can break this down into the sum of two integrals. And then clearly these are constants of integration, so we can split out the constants here. And then if we look at what's left over, we have the operator on f1. So from this definition, it's the function multiplied by g integrated in time, which is indeed the definition of the operator. And we get the same here for the second function. So we can rewrite it like so, and if we look at this overall result, we can see that is an important property for linear operators to have. So yes, even an integral action is still a linear operator. So we introduced the Laplace operator, and that's the form. So it's this factor e to the minus st, so that's the function g that we are using, and we are integrating from 0 to infinity. So we want to show the transformations of the Laplace operator on various important functions in time. And before we do that, we note that there are some operations that we will use quite often in this formulation. So to make progress with all the transformations we're going to look at just now, there are a couple of recurring things that we should take note of. Number one, let's just treat s as a constant. So we won't consider that s is related to t in any way. It's seen as just a constant here. And it's just a parameter in this transformation. So in the integrations, we can easily split out s depending on the type of function. The second thing is we should note that the integration by parts formula is going to occur many times. So we remind ourselves the integral of fg is f integral g minus the integral of the derivative of f multiplied with the integral of g. So the integration by parts formula. And then the third thing, this is kind of an obvious one, but if you take the integral of e raised to the power at integrated in t, then that integral is of course 1 over a e to the at. So of course, if you differentiate that, a times 1 over a is 1, and e to the at. So with those three basic things, we pretty much cover all the transformations we'll see. So let's get into it. If f of t is simply a constant k, then the Laplace transform of this f of t, which we denote like this, so the result of the transformation we'll call y of s. So capital Y is the typical convention, and S is now the parameter. So the way we say it is that we are transforming a function in the time domain to another function in the s domain. So the Laplace transform of a simple constant, of course, is going to be e to the minus st times that constant integrated from 0 to infinity. And now, of course, if you integrate the exponential, it's going to be 1 over the coefficient. So it's minus 1 over s. And then k is a constant with respect to t, so it's minus k over s. And then e to the minus st between the limits 0 and infinity. And of course, at infinity, this is e to the minus infinity. And that's, of course, a 1. That's a 0. So we have a 0 here. And then minus the lower limit. So at 0, this is e to the 0, which is a 1. And then we've got minus k over s. So that's minus k over s. So we're left with k over s here. So the Laplace transform of the constant k is k over s. So that's the first one. Then if we think about the step function, so here we have that for values of t less than 0, the function is a 0. If it's more than or equal to a 0, it's a 1. So that's the discontinuous step function for f of t. So if we stick that into our Laplace transform, then clearly we are not integrating below 0. So in fact, this doesn't make its appearance at all. We don't see that 0. We only see the 1. And that's 1 times e to the minus st. So the expression simplifies quite easily to this form. And again, we integrate on this exponential. So it's 1 over the coefficient of the integration variable. So it's minus 1 over s times e to the minus st, integrated from 0 to infinity. And here, if we have exponential of minus infinity, that's a 0. And then minus minus 1 over s e to the minus st. At 0, e to the 0 is a 1, leaving us with a minus 1 over s. And then it was minus that, so we are left with 1 over s. So in other words, for this discontinuous step function, which just gives us a 1, we get 1 over s. You can also think about it in the context of the previous case with the constant. You could say, well, since the discontinuity is at 0, we actually don't even see this this part, the 0, so we just see a 1. So you could view this step function as a special case of this case where it's a k. So you could say k equals 1 here. So you get the 1 over s, which is what we have here. So the step function y of s for the unit step is 1 over s. Now, slightly more general than that case, the rectangular pulse function is 0 for t less than 0. It has a value of k for t between or from 0 to, but not including tw, and then if it's 0 after tw. So if you imagine this, I'm not going to draw it anywhere, but you can imagine it's 0 and then goes up to k and then comes back down to 0 after tw. So that's the function. And then clearly here you can see that this function is non-zero only between 0 and tw. So in our transformation, we might as well integrate just between 0 and tw. And at that point, f of t is simply k. So we can simplify to a k here. And k is, of course, a constant of integration or a constant in time, so we can split that out. And then we have, again, an integral of e to the minus st, which is 1 over s e to the minus st. And this time, however, it's not from 0 to infinity, it's 0 to tw. So in the upper limit, we have to retain this. It's not like it goes to minus infinity or anything. We have to keep this e to the minus stw. And we retain the coefficient there, k over s. And then at 0, this is a 1, and it's minus k over s. So this becomes a plus k over s, and we take that out in front, and we group out the k over s here, and that's what we get. And so you have this exponential saturation style factor here when you have a rectangular pulse function as your origin function. Right, so that's the Laplace transform for the rectangular pulse. Now for the impulse function, of course the impulse is represented with the Dirac delta function, and the Dirac delta function is a critical function. It's really facilitated many theoretical developments in physics especially. So the Dirac delta function looks like this, that when t is not equal to 0, the Dirac delta function is 0. So it's really 0 most of the time, except at one very special value. So when the argument is a 0, then this function goes off to infinity. And it goes off to infinity in kind of a special way. It goes off to infinity such that if you integrate under that 0 instant, you get back an area of 1. And a way to think of this function is if you have a normal distribution and you take the limit for the variance going to 0, then that normal distribution will get sharper and sharper. But being a normal distribution, its area always integrates to 1. So you could say that this is a special case of the normal distribution. But of course, it isn't really. It is a true discontinuity, and anyway, we work out the Laplace transform of this by noting that we have this other known property, that if you take the impulse function, if you take the Dirac delta function and multiply it with another function, so the other function also has one argument, but you shift that argument by a certain amount. So let's say function f was a function of time, and then let's say we shifted that time by an amount a. Then if we think of it, if we graph function f of t and then we shift it by an amount a, and then we multiply by the Dirac delta function, then this function is going to zero out all values of f except for the value at t equals 0. And so when we integrate over that function, the only surviving value is going to be f of a. All right, so if we use this property in our transformation, we can see here that this is going to result in the function that we are multiplying with at the specific value t equals 0. So this is e to the minus st at t equals 0, and of course at 0 that's e to the 0, which is a 1. So the Laplace transform of the Dirac delta function is simply 1. All right, the fifth one is the ramp function. So in the ramp function, our f of t is simply kt. So it's increasing at a constant gradient or constant rate, which is k. Right, so f equals kt, and if we transform that, then it's kt e to the minus st. And if we want to integrate this, we can select t as the function. Well, let's go back here to the notes we made earlier. So remember, integrating by parts, we identify two functions. So we have to choose one function as f and one as g, and then once we do that, we use this formula. And typically, when we are trying to decide what should be f and what should be g, we would choose f to be a function that tends to disappear when you differentiate it. So polynomials, for example, if you differentiate them enough, then they go to constants and to 0. And exponentials also repeat themselves, so you can think about some simple algebraic solving if you can get a function to repeat itself. Anyway, we'll see what I mean by all that here. So if we are taking f to be t, then we know that the solution to this is f integral g. So we split out kt here, and then the integral of e to the minus st is 1 over s, or rather minus 1 over s. And in fact here I need to write this as a minus, right? So that's minus 1 over s times kt, and then e to the minus st, and we are integrating between infinity and 0. So we park that as the first term in our integration by parts formula. And then for the second part of that, we take the integral, and here of course we've taken out k as a constant already, and then it's the derivative of f. So f we chose as t, so it's dt dt, which is a 1, so there's a 1 here. And then it's the integral of g, so integral of g is of course going to be the integral of this factor here. And then if we perform, so we'll park this result, and now let's go back to this term. So if we go off to infinity, it's e to the minus infinity here, which is 0. And then at 0, we've got t equals 0 here. So this whole thing is a 0. So it's 0 minus 0. In other words, this part of the integration by parts contributes nothing to the overall integral. And then from here, there's still a bit of work to do. So here we can integrate this part. We can say this is 1 over s, or minus 1 over s times the constant. And I see here there's another, this should be a plus now, and then that's the result of this inner integration, and then we still have to integrate that one more time, and again it's going to be minus 1 over s times that. So we know that's a 0 right there. And then if we perform this integration, we can split out a minus s in front here. And of course, we are integrating here in t. We should have said dt. And because s is a constant in t, we can indeed split that out. And so let's not write the 0. So we've got your minus k over s squared. And then we still have the e to the minus e raised to the minus st. And we are integrating here from 0, lower limit 0 and upper limit infinity. All right, well, I'm just going to leave it like that, and let's just talk through it. So here at the upper limit of infinity, this is going to be e to the minus infinity, which is 0, so we can forget about the upper limit, minus k s squared or e to the minus st at 0. So at 0, this is e to the 0, which is 1. So this is leaving us with the k over s squared. So that's the lower limit, minus, and then minus, and that leaves us with a plus k over s squared. So for the ramp function, we are getting k over s squared. Moving on now to the exponential itself. So if our function is e to the kt, then in our transformation, e to the minus st times that. Of course, we would group those together. So grouping the t, it's minus s plus k times t. And when we integrate that, of course, the s and k are constants in time. So it's minus 1 over s plus k, e to the minus s plus kt. And from 0 to infinity, at infinity, this is x of minus infinity, which is 0. And then at 0, this is e to the 0, which is 1. And then it's minus 1 over s plus k, so it's 1 over s plus k. So for the exponential itself, we have 1 over s plus k. And this is quite an important one. We'll often see ourselves using this transformation. It's extremely useful. And just to comment on it a bit more, if you have a time function, the constant of that time function appears in the denominator as s plus k. So when you transform an exponential in time, then the coefficient of that exponential, of the time part of that exponential, that coefficient shows up as an argument or as a parameter which shifts s, and it's 1 over s plus k. So that's one thing to note. Another thing is our input here is a transcendental function, whereas the output here is something like a polynomial. So this is something we can do easy algebra on. This is something that takes a bit more work. So those are just things to keep in the back of our minds, but we'll see later on we can really exploit those properties. So that's the transform of the exponential. Looking then at first order differentiation, if we have the function this time as df dt, right? So the time function we are putting in is actually the derivative of some other function f, right? So note here, this transformation is not a transformation of f itself. It's the transformation of the derivative, the time derivative of f. So right, of course, if we apply the definition, that's what we have. And then from our integration by parts, right, and you see I've written it slightly differently to how we wrote it before, but it's the same thing. So we are choosing the first function as e to the minus st, right, the operator kernel, and b as this derivative function. Then if we apply that in there, that integral is going to look like, of course, a we just multiply by that function, and then for b we have to integrate df dt. So we are integrating in t, right? Remember the transformation is to integrate out the time. So we are integrating df dt with respect to t. So that's nothing but the function itself and over those limits, right? 0 to infinity. So that's the first term. And then for the second term, we've got the derivative of the function. And so this is going to be minus s e to the minus st, right? This is the derivative. We were integrating before. That's when you have 1 over s. Now that we are differentiating, it's just going to be minus s e to the minus st. So, of course, the second term, there's a minus, but when we differentiate, then that's a minus s times a minus, so that's a plus s there. And we need dA dt, so we've differentiated, and that's what's still in there. We keep the exponential there because it's a function in time still. And then we have to still integrate for this inner part. We still have to integrate this b, which again is that derivative. So this is simply f itself. And now when we look at this, we can recognize this part as nothing other than our transformation, right? And of course, this is a transformation of the function f. It's not the transformation we are looking for, because the transformation we want here is the transformation of the derivative. This is the transformation of the function itself. So we'll just call that a y primed, right? And this doesn't mean differentiate with respect to s or anything like that. This is just y dashed to say this is the that this is y, which is composed from f, not df dt. So that's the second part of the integration by parts. So coming back to the first term, we now have to evaluate between the limits. When t goes off to infinity, we've got e to the minus infinity, that's a 0, so that's there. And then when t goes to 0, then that's e to the 0, which is a 1. And then f is also a function in t, And so if we are applying 0 here, then this is f at 0. In other words, this is the initial value of the function. Right, so the first part of our integration by parts gives us just the initial value of the function that we are trying to differentiate. And then if we look here, as we said, this part we are just calling y dashed. Right, so s did appear as a constant, so s y dashed. And so that's what we get if we take the Laplace transform of the derivative of a function. We get sy dashed minus the initial value of the function itself. Right, so if we are interested then in higher derivatives, let's say it was the second derivative that we were interested in, then we would apply the same approach of integration by parts, and we would choose again the exponential function as the a of t and the second derivative as the b of t. And here clearly we'll get this form. So we would integrate d2f dt squared, and for the second part, again, the s will split out when we integrate this, differentiate this part, and then we integrate this part, and that's still in the overall integral. And then evaluating this at infinity, that's a 0. At 0, that's a 1, leaving us with minus df dt at t equals 0. And then this s here, now we can see here that this is the same as the first order case. Right? If you go back here, we were looking for the Laplace transform of the derivative of f, which is the same as what we just looked at. So we know what this is going to be, right? We have s y dashed f at 0. So we can see that's going to appear here, and it's going to be s times all of that. And so for the second derivative, the Laplace transform of the second derivative, it's going to give us the derivative at t equals 0 plus s times the first derivative's transform. And you can see a kind of recursive pattern appearing here. And as you might anticipate, we can, by induction, deduce what this is going to be for the Laplace transform of the nth derivative of f. Right? So if you follow the pattern, you get something like this. So you can say for the nth derivative, it's simply going to be s to the power n times fs, and then we will have several terms after that, which will be the derivative of not the derivative. It's going to be s to the n minus 1 times the initial value minus s to the n minus 2 times the first derivative. So that's the notation. The brackets with the number tells you how many times you differentiate this function, and this is time differentiation, of course, and this is evaluated at t equals 0. So you get a long list of factors like that there. So you can now evaluate the nth order derivative, and again, we are getting a nice algebraic form here. So all the derivatives disappear, leaving us with, there is one f of s, and this one is easy to get, right? If we know the function f, then we can find this, we can find the transform. So this should actually be f dashed, right? Similarly here, that was supposed to be f dashed, because that's the transform of f itself. And then we've got all these other terms down here. So it looks symbolic and kind of mysterious, but when we look at the examples, we'll see this is quite easy to work with. All right, so those are the sort of calculus style functions. Let's look at some trigonometric ones. Of course, we know this from complex math. We know that the cos of omega t is e to the I omega t plus e to the minus I omega t over 2. And so if we perform the Laplace transform of cos of omega t, that's going to be a half Laplace transform of e to the I omega t plus a half Laplace transform of e to the minus I omega t. So here, of course, we are using the property of linearity of the Laplace transform, and now we have already considered this. We've already looked at the Laplace transform of the exponential, right? We said here that the Laplace transform of an exponential with a constant for the variable was going to be 1 over s plus that constant. And we can just use that here. So it's going to be 1 over s plus, the constant here is I omega, and then plus a half 1 over s plus the constant, which is minus I omega. And of course here, if you look at these are kind of complementary denominators. So we can, if we multiply these two together, we know we'll have s squared plus minus the square of I omega, which is going to be minus omega squared, and so minus that is going to be s squared plus omega squared, and then if you multiply that by this factor, it's what will be left over here is s minus I omega, so that's there, and then we multiply here, what will be left over is s plus I omega. And then here you can see the minus I omega cancels with the plus I omega. And this is s plus s, which is 2s, that can cancel with that too, leaving us nicely with s over s squared plus omega squared. So the Laplace transform of a cos is simply s over s squared plus omega squared. And again, you can see a transcendental function which is now converted nicely into a polynomial type function that we can easily do algebraic operations on. So that's for cos. And then if we look at delay times, so let's say we have some function in time, and let's say that this function gets delayed by time t naught. So if we imagine some function in time that gets shifted by t naught, that it takes an extra time t naught before we can start seeing that function, then that's a delay. And we want to zero out the time. We want to specify that we want to set the output of this to be 0 for, we don't want, if we have times less than t naught, we don't want to find values and send those back out to our delay function. What we want to say is let this be 0 if we are less than t naught, and then after t naught, that's the function. So it's graphed better than I'm saying it here. You can see if that's your original function f of t, if you want to delay this function, if you want to say let it be t naught before this function appears, so we can just shift that function along by t naught. Now if we send in values, let's say at a half t naught, then we would be looking up values before 0 here in our original function, and we don't necessarily know that. So an easy way to fix that is to say just multiply it by the step function, and this is the step function shifted also by t naught. So we force the function to be a 0 before t naught, and it's a 1 after t naught, and so the product here is this delay in time. Right, so that's delay. And now if we use this function in our transformation, right, so we've just multiplied it here and multiplied by e to the minus st as normal. First off, we can see that this function is going to be 0 for all time before and equal to t naught. So it's 0 here. So instead of integrating from 0, we might as well start integrating at t naught. And then we don't have to worry about the step anymore. The step is only before t naught. So we've got this delay. And now what we can do is introduce a factor. So let's say we arbitrarily introduce this additional constant. So we can think of t naught as a constant, right? It's not changing in time. It's a fixed instant in time. So let's say we multiply by e to the minus st naught, right? Then if we want this equality to be true still, then we also have to divide by that amount, right? In other words, we want to multiply and divide by the same value here. So to divide by this value, we would put in the e to the plus st naught. And that's what we do here. So we had here e to the minus st. We are now dividing by e to the st naught. So that when we compile it together with the original e to the minus st, then we get simply a shifted time over here. So we know these are all constants in time, so we can split that out as a constant of integration, leaving us with s times t to the minus t naught. This function is also f of t minus t naught, so you can see t minus t naught as a shifted value. Now we have also, because we are starting from t naught here, we can change this, and in fact we've already changed the variable here. So okay, let me explain this a bit differently. T naught is a constant in t, so we can rewrite this variable as t minus t naught, because if we differentiate t naught with respect to t, that's of course a 0. So we can rewrite this dt as a dt minus t naught. Right, so we can see everything that has a t in it is now shifted by t naught. And so we can rewrite this whole thing as a new variable t dashed, right, which is t minus t naught. And in fact, down here, this should now be a 0. And so if we examine this, this is now a Laplace transform, right? It's integral naught to infinity. It's in a new variable, but it's just a change of variable. So this is the Laplace transform of the function without shifting time. And so the impact of a time shifted function is simply an exponential in t naught of the Laplace transform of that function. So here let's list that as e to the minus s e to the minus s t naught times y dashed of s, and of course this is so this is the Laplace transform of the original function without time shifting, and we just have to multiply by this exponential of the time shift itself. And that's quite a useful result, right? Normally we deal with time shifting by having to move the whole argument and so on. In the case of the Laplace transform, the time shift actually appears as simply a factor in front of the Laplace transform of the unshifted function. So that's quite a simple way to handle time delays. Okay, we're not done yet. Integrals, right? If you are trying to find the Laplace transform of the integral of f, then of course again our integration by parts is useful. So just applying the definition of the Laplace transform, it's the integral naught to infinity e to the minus st of the function itself. In this case, it's the integral function. And again, let's see what a good choice in this case would be to use this as the first function, right? Remember, the first function is going to be differentiated. So it's we can see that if we differentiate this function, we are going to get f itself. And so we choose that as the first function for integration. So in terms of our integration by parts formula, we will first just transcribe the same function without a change, so that's there. And then we have to integrate the second function. So we do this integral, so it's minus 1 over s e to the minus st, and then the limits here not to infinity as usual. So that's the first term dealt with. And then for the second term, it's minus, and then it's the integral of the derivative of the first function. So the derivative here is obviously f of t itself. And then we multiply that by the integral of this, which is minus 1 over s e to the minus st. And then we move the 1 over s out here, and the minuses cancel, and we bring in the e to the minus st here. And here at infinity, it's e to the minus infinity, which is 0. At 0, this is, well, in fact, at 0, we are integrating naught to 0 here. So actually, because the integration range is 0, right? It's we are integrating from 0 to time t, and t is 0 now in the lower limit. So this is the integral over 0 of a finite function. So this is going to be a 0 itself. So it's 0 times whatever this is. And in fact, this just then becomes a 0. So this term, like before, doesn't contribute anything to the final integral. Not like before. Before with the derivative, it did contribute the initial value. So anyway, so in this case, this is zeroed out. And then here, we recognize that this is now the Laplace transform of f of t itself. So it's 1 over s y dashed, right? It's not the Laplace transform of the integral, but we can easily relate that Laplace transform to the Laplace transform of the function itself. So for integration, we have this interesting result here, that the transforms of the integrated and unintegrated forms are related by a 1 over s, right? And so again, you can see a fairly complicated operation in the normal time domain actually has a much simpler representation in the s domain, right? Just a 1 over s. So this starts to imply to us that maybe the Laplace transform is giving us a different perspective on our usual complex calculus operations. Okay, so we can regard these 11 transformations as primitives that we can use in that we can use to construct the transformations of more complex functions. And in fact, we have a lookup table here with more complicated functions involved. And we're not going to go through the derivations for all these, because in fact, you can do all these as linear combinations of these 11 base types. So we have this nice table of about 26 transformations. And you can see here, even though you tend to have complicated functions on the left-hand side, the S-domain version of it is quite simple. And almost all the time, they are polynomial-style equations, right? Here's one case where you have some trigonometric functions. We know for the time delay, we get an exponential. But otherwise, these all look very polynomial. And it's not often that you find transcendental functions here. So it looks like it's much easier to work in this S domain. And another thing we should think of is, well, if we have a function in the S domain, we could use a table like this to look up the equivalent time domain problem. And so a table like this can imply to us that, well, what if we could take our original mathematical problem, translate it into the S domain, perform some algebra on these expressions. So maybe we get a sum of terms in the S domain, and then after simplifying those expressions, we get an expression here. Then we can just look up the equivalent. We can invert that and look up here on this side. Well, what's the equivalent time function for that? And in other words, that would be the solution to our original problem, which was in the time domain. So this is, it starts to look quite promising in terms of solving differential equations. And that's exactly what we'll do now. Just a few notes here first. Well, these are things I've been saying: transcendental to polynomial, also periodic to aperiodic, right? This original time function, that's a periodic one. So no matter how far you go in time, this function will be jumping up and down. Whereas here you can see this is going to saturate at some point, and so you are changing the periodicity of the function during this transformation, and that we anticipate may have some benefits in terms of trying to transform our equations and analyze our equations and so on. We've sort of said some of the things here. The third and final thing I wanted to say here is that the time constants, right? Let's go back to the table. Let's look at our time domain functions. You can see here this factor bt, right? That b is an exponential factor here. It's showing up here in the denominator. Here, e to the tau, you can see the tau there. Well, in fact, most of those are exponentials, which are all showing up as other factors there. Here's a sine wave. So in the sine, you've got that omega, and that omega is showing up here. So if you look at it, many of these are in the form of some denominator. And let's go to the simple case here. We can regard this value as giving us a pole, right? When s is minus b, then we have a zero in the denominator. And so that's why we call this a pole, right? S equals minus b is a pole. It's a region where this function goes off to infinity. So that factor of a minus b is appearing here as a time constant in the time domain. So our time domain functions, their time constants show up as poles in the S domain. And that's a tremendously useful property which we'll exploit again and again in developing controllers. So once more, the time constant in the time domain shows up as a pole in the S domain. It shows up as a value which causes the function to go to infinity. Right? So let's look at solving some differential equations now. So let's say we have this differential equation. It's a first order equation. It's not homogeneous, and we have an initial condition here. So initially, the value of y is 2, and the rate of change of y is, well, you can take that across and so on. Anyway, let's just solve it in this form. So if we find the Laplace transform of this, because this is a linear operator, the Laplace transform is linear, we can just Laplace transform each factor, or rather each term in this equation. So the Laplace transform of this, we regard the two simply as a factor, and so it's Laplace transform of y of t, and then 3 times Laplace transform of y, and then Laplace transform of 4. And then the initial condition. We know the Laplace transform of the derivative is sy minus the initial condition, and then the Laplace transform of y, we just define that as a capital Y, and then Laplace transform of 4 of a constant is the constant over s. So in the Laplace domain, this is simply twice the Laplace transform. So Laplace transform here, sy minus the initial condition. The initial condition is 2, so it's sy minus 2, and then 2y, so that was just 3 times y there, and then 4 over s. And if we look at this, we can see we can group out the y. So y times, and this is 2s plus 3 equals 4s here. And let's see, we also have a 4 here. So 2 times minus 2 is minus 4, and then we take that across, so that's a plus 4. And here we are just grouping 1 over s here. So we took out this factor of 1 over s. That means we have to include an s here for this to remain true. So it's 1 over s times 4 plus 4s equals y times 2s plus 3. And so we can say y equals 1 over s times this stuff. So 1 over s times that divided by 2s plus 3. And here we can just we want to write this as an s here, so we group out some of these constants a little bit, and then we can just look this up in the transformation table. So look for this general form. We've got s plus something divided by s times s plus something else. And so if we go look up in the table, so right here, so we can identify that this must be the time domain version of this function. So just applying that in there, we can see that that is the solution to our equation. And so look at what we've done here. We had originally a non-homogeneous first order differential equation, and we haven't done any calculus here. All we did was a little bit of algebra and then a table lookup, and now we suddenly have a solution. So that's the great power of Laplace transform when solving differential equations. We can very rapidly look up a solution, and in fact we won't even really be using the superpower. We'll actually be using this more for analysis. But anyway, that's how you can use Laplace transforms to solve differential equations. We will actually be spending a bit of time on solving differential equations with Laplace, but that's just because we'll make a bunch of observations which will be useful towards analysis just now. You should also read the notes on partial fraction expansion. So sometimes you get a form which is not obviously a form that you can look up in the table, and there are ways to transform your equations into a form that's friendly to table use. So here, if you get a high order term like this, you just go ahead and use the formula that we saw earlier to get it into the S domain, and then you tend to end up with factors like this. And you can find the equivalent form of a factor like this. If you say, well, if I have a factor like this, there will exist some expansion like this. So this is just your proposal that there must exist a way to separate this term into two terms like this. If I include constants here, so it's just a matter of finding those constants. And so if you do that, you multiply that out and you choose S values which zero out certain numerators, then you can separate those into factors which you can then look up. So you might not have this in the Laplace table, but you can look up factors that have those forms. Right? So there are many examples you can find for practicing Laplace transformation. More generally speaking, you can invert an S function. So you can invert it using this general Mellon's inverse formula, or the Bromwich integral, or the Fourier-Mellon integral. So the inverse Laplace transform of an S-domain function looks like this: 1 over 2 pi I integral alpha to the minus I omega alpha to the plus I omega, and then E of st. You probably expected to see that. So that's how you can invert if you aren't able to use tables or something like that. That's an inversion formula. And a tremendously useful property of this is if you have an S function which can be expressed as a sum of S functions, then the inverse transform of that original function is the sum of the inverse functions, right? So this is an unexpected result, and I know Laplace transform is a linear operator, but it's linear in the case of transforming f of t. But its inverse also has this property that you can break this down, and that's a tremendously useful thing. And if you've done enough examples in solving differential equations using the Laplace transform, you'll see why this tremendously extends the range of functions that of problems you can solve using Laplace transformation. Okay, so that's pretty much it. As I say, one does need to practice many problems to really feel confident in this, but these are all the basic elements that we need